In an earlier installment of our linear algebra primer, we saw that any matrix can be thought of as representing a linear function. What we'll see today is that if the matrix is square, so if it has the same number of rows and columns, then it also represents a quadratic function. So today is going to be all about square matrices and their properties. So let's start with a special case that we saw before. So one thing we found is that if you have a vector x, then x transpose x is just another way of writing the dot product of x with itself, which is the length of x squared. In fact, you can also think of this as being x transpose times the identity times x, because the identity times x is just x. Okay? Now the identity matrix is just a d by d square matrix. What if, instead of having the identity there, we put some other d by d matrix in the middle? What if we use x transpose mx, where m is just any arbitrary d by d matrix? What do we get? Okay, so let's take a look. So we have x transpose, that means takes x and make it into a row. We have this matrix M, which is d by d. And then we have just x, which is a column. So what are the sizes? Here we have 1 by d, here we have d by 1. And so when we multiply things, we see that the inner dimensions agree. And the result is simply going to be the outer dimensions, which is 1 by 1. So the result is just going to be a single number, as we expected from the case of x transpose x. So the result is a single number, and in fact I'll give you a formula for the number. It turns out that if you just expand this out, it's quite simple to do. It turns out to be the sum over all I and j of mij xi xj. And this is a quadratic function of x. Okay? So each of these terms, it's a sum of a whole bunch of terms. Each of these terms has got some mij. That's just a number from the matrix M. Okay, some number like 2, 3, 4, and so on. But the dependence on x is quadratic. There are pairs of terms from x, xij, or also some terms like xi squared. Let's see a specific example of this just to drive the point home. Okay, so what if we have a matrix that's 2 by 2? What kind of quadratic function does this represent? Well, if the matrix is 2 by 2, these vectors x have to be two-dimensional. Okay, so the function we're talking about is x1, x2 times this matrix times x1, x2. And we can just expand this out. Okay, so let's start by doing this part. Okay, so we'll copy over the x1, x2, and let's just simplify the matrix times the vector. What do we get? We get x1 plus 2x2 and 3x2. So now we're multiplying together these two. And this is just a single dot product. It is x1 squared plus 2x1 x2 plus 3x2 squared. And this is certainly a quadratic function. All the terms in here are quadratic. x1 squared, x1 x2, x2 squared. Okay? Let's actually go back and see how this squares with the formula I gave you earlier. This whole thing with the sum over ij of mij. Let's just copy that down and see that we actually get the same thing. Okay, so I said that it should work out to mij xi xj, the sum over all ij. Okay, so what are I and j in this case? Well, it's just two-dimensional, so they're going to run over 1 and 2. So this is equal to m11 x1 x1. Let's just write out all the terms. m12 x1 x2, m21 x2 x1, plus m22 x2 x2. Now we can go in and plug in the entries from the matrix M. Okay, So what's m11? That's 1. Okay, so it's x1 squared. What's m12? That's this entry over here. It's a 2 plus 2x1, x2. What is m21? That's a 0. And m22 is a 3. And so you can see that it's exactly the formula we got simply by expanding out. And in fact, that's how you get this summation. If you just do what we did before, but in greater generality. You allow it to be d-dimensional, and you allow m to just consist of variables that haven't been defined yet. Okay. So here's a summary of the formula. Okay. If you start with any square matrix M, you can define a quadratic function by mapping x, a d-dimensional vector, to the number x transpose mx. And it works out to this summation over here. Okay. The summation actually lets us read out the quadratic function very easily. Okay, so for example, we have this matrix. What is the quadratic function associated with it? It's something that sends three-dimensional vectors to a single number. So you have three-dimensional vectors, x1, x2, x3, and they get sent to what number? Well, m11 is 1 times x1 squared. Then we have m22 times x2 squared. Then we have m31 times x3, x1. Then we have m32 times x3, x2. And then we have m33 times x3, x3. That is the quadratic function associated with this matrix. We can also try to reverse engineering things. Okay, so here we have a quadratic function that takes a two-dimensional vector and just returns a number. How do we write this function using a matrix? What is the matrix that corresponds to this? Okay, well, these are two-dimensional vectors, so we're going to need a 2 by 2 matrix. And so we have to fill in these 4 entries over here. Now, just from the fact that the leading coefficient here is a 1, we know that this must be a 1. From the fact that this coefficient for x2 squared is a 3, we know that this must be a 3. But it's not clear what these two numbers have to be, so let's just call them a and b. Okay, so what we know is that a plus b has to be equal to 2. And so there are actually several ways to achieve this function. We could use a matrix like 1, 2, 0, 3, or we could use 1, 1, 1, 3, or we could use 1, 0, 2, 3, and so on. There are actually infinitely many possibilities. Okay? So there are many matrices that realize this particular quadratic function. Okay. So we've been talking about square matrices. A special type of square matrix is one that is symmetric, one that is equal to its transpose. Okay? And what this means is that the matrix remains the same if you reflect it in the diagonal. Here's an example of a symmetric matrix. Okay? If you reflect it in the diagonal, 2 comes back to 2, 3 comes back to 3, 5 comes back to 5, so it's symmetric. The second matrix over here is not symmetric. Look at this 1 and 2, for example. Okay, so this is a non-symmetric matrix. It turns out that many of the matrices we'll be dealing with will just automatically turn out to be symmetric, and this will simplify things quite a bit. Now, an extra special case of a symmetric matrix is one that is diagonal. A matrix whose only non-zero entries are along the principal diagonal. Okay, so one like this. So a diagonal matrix is 0 everywhere except along this diagonal over here. And as a result, there's a very compact way of writing such matrices. Since there's no point using d squared entries since most of them are 0. We sometimes just use this shorthand over here. Okay. Now, one of the key quantities associated with the square matrix is the determinant. So if we have a matrix A, the determinant is just some number, and we represent it using these bars. Okay, so we put these bars around A. And you might remember from high school or early college that the determinant of a 2 by 2 matrix, ABCD, is AD minus BC. Okay, so for example, if we have this 2 by 2 matrix over here, the determinant of A is 3 times 2 minus 1 times 1, which is 5. Okay, it seems a little bit random. Does the determinant actually mean anything? So it turns out that it does. Okay, so let's look at this specific matrix. Let's think of the rows of the matrix as being data points. Okay, so we have these 2 data points. And let's just go ahead and plot these points. Okay, so we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, the first point is 3, 1. The second point is 1, 2. Okay, so we've gone ahead and we've plotted those 2 points. Now, let's take these 2 points and extend them to get a full parallelogram. Okay, so we had this 3, 1, and now we take another 1, 2, and we come out here. So now we have a parallelogram. What is the area of this parallelogram? It turns out to be 5. That's what the determinant is. If you think of each row of the matrix as being a data point, and you plot those points, and you create the parallelogram, the determinant is the area of the parallelogram. And this works not just in 2 dimensions, it works in d dimensions as well. If you have a d by d square matrix, you look at the rows of that matrix, you plot those points in d-dimensional space, you extend them into a parallelogram. When it's in higher dimension, instead of being called a parallelogram, it's called a parallelepiped. So you extend it into a parallelepiped. The volume of that object is the determinant of the matrix. Okay, so let's actually go ahead and check that. With an example, we probably with an example that would be familiar to us. What if we take a 3 by 3 matrix, okay? Like let's take this matrix over here. Let's go ahead and plot these points in 3D. Let's say A, B, and C are positive, okay? So we have our 3 axes, x1, x2. I'll just draw the third axis over here, x3. So along the x1 axis, our first point lies along the x1 axis, it's A. Our second point lies along the x2 axis, it's B over here. And our third point lies along the x3 axis, so it's C over here. Okay? And now we extend this into a 3-dimensional body. Not very good artwork, I'll confess. Okay? What is the volume of this thing? Well, we know this. The volume of this is just ABC. Okay, now let's go back to what we were saying about determinants. Is the determinant of this matrix ABC? Indeed it is. The determinant of a diagonal matrix is just the product of the diagonal elements. Okay, so a very important quantity associated with the square matrix is the inverse. Okay, so if you have a square matrix, a d by d matrix A, the inverse is some other matrix B, such that A times B is the identity and B times A is the identity. So what this means, among other things, is that B has to also be a d by d matrix. Okay, and the notation we'll use is that we'll call this matrix B, we'll just call it A to the minus 1. The inverse of A. So let's do a little bit of an example. So Here's a 2 by 2 matrix A, and I'm claiming that this particular matrix is the inverse of A. Okay, so let's check and see if this is really the case. So 1, 2, minus 2, 0, that's A. And the thing that I'm claiming is the inverse is 0, minus a half, and a quarter. Let's see what this multiplies out to. Okay, so the first row of A times the first column of B. Okay, so we get 1. The first row of A times the second column of B, we get negative a half plus a half, that's 0. The second row of A times the first column of B, we get 0. The second row of A times the second column of B, we get 1 plus 0, 1, which is indeed the identity matrix. So this is the inverse. Now there are a few things about inverses that really should be emphasized. First of all, they don't always exist. There are many square matrices that don't have an inverse, and we call those matrices singular. Okay, so a matrix is singular if it's not invertible. And it's something fairly common. Okay. The second thing is that there's an easy way to assess singularity. A matrix is singular if its determinant is 0. Okay, so another way to put it is a matrix is invertible if and only if its determinant is non-zero. Okay, and so now let's look at a special case. Suppose we have a diagonal matrix, A1 to AD. What is its inverse? Okay, so we have a diagonal matrix, A1 to AD. If you remember the notation, it means that this is the matrix we're talking about. All the entries off the diagonal are 0. It's a D by D matrix. First of all, can a matrix like this ever be singular, non-invertible? Yes, it can. Okay, so if you recall, the determinant of a matrix like this is just the product of all the diagonal entries. So it's A1 times A2 all the way to AD. And we want this product to not be 0. Okay, so we need all the AI to be non-zero. If that's the case, then the determinant is not 0 and the matrix is invertible. And what is the inverse? Well, it's very simple. You just invert each of the diagonal entries. And that's the overall inverse of the matrix. Okay, well that's it for the third installment of our linear algebra primer. This is going to hold us for a little while, so we'll give it a week or two to sink in, and then we'll come back in a little while and do a little bit more linear algebra.